Fundamentals of array-based storage in Python. Arrays provide contiguous memory storage for elements of the same type, making them ideal for fast random access. In Python, while native support exists for dynamic arrays through lists, developers must understand trade-offs between flexibility and efficiency. The built-in list type allows variable length sequences, automatically expanding capacity when new items exceed current limits. However, this dynamic resizing introduces overhead during frequent insertions or deletions from arbitrary positions. Time complexity. Accessing elements takes O(1), while inserting/removing may require O(n) due to shifting operations. Memory allocation. Pre-allocating fixed-size arrays avoids resizing costs but restricts growth potential. Python's implementation uses amortized constant-time complexity for append operations, ensuring average case efficiency even with dynamic expansion. Developers often leverage array modules for stricter type enforcement and lower-level control. Numerical computations benefit significantly from number-py arrays, which enable vectorized operations and optimized memory layouts. These specialized arrays offer faster processing compared to standard Python lists for mathematical tasks. Linked lists and their memory management implications. Unlike arrays, linked lists consist of nodes containing data references rather than relying on contiguous memory blocks. This architecture enables efficient insertion/deletion but incurs higher access times due to sequential traversal. Singly linked lists maintain pointers to subsequent nodes only, while doubly linked variants add backward references for bidirectional navigation. Circular links create closed loops useful for certain queue implementations. Performance considerations. Average case analysis shows O(1) insertion/deletion at known positions versus O(n) for arrays. However, accessing arbitrary elements becomes O(n) since traversal starts from head node each time. Space utilization differs significantly between implementations. Arrays waste space when elements don't fill entire allocated blocks, whereas linked lists consume additional memory for pointer storage in every node. Python lacks direct syntax for manual linked list creation, requiring explicit object-oriented definitions. This approach emphasizes encapsulation while demonstrating low-level memory management principles. Stacks and queues. Core concepts in algorithm design. These linear data structures govern element ordering according to strict rules: last in first out, LIFO, for stacks, and first in first out, FIFO, for queues. Understanding their characteristics is vital for recursive function calls and system resource management. In Python, stack behavior emerges naturally from list append/pop operations, though deque objects optimize for queue semantics with efficient front-end modifications. Custom implementations reveal underlying mechanisms governing these abstractions. Application areas. Stacks power expression evaluation, backtracking algorithms, and browser history tracking. Queue uses. Task scheduling, breadth-first searches, and message queuing systems rely heavily on queue mechanics. Differentiation lies in operation order: pushing adds to top, popping removes from top, enqueuing appends to end, dequeuing retrieves from beginning. These distinctions shape algorithmic approaches across domains. Implementing custom versions exposes limitations inherent in standard library implementations. For instance, standard list-based stacks suffer from O(n) worst-case pop operations when resizing occurs mid-execution. Hash tables, enabling fast lookup operations by mapping keys to values through hashing functions. Hash tables facilitate near-constant time complexity for insertions, deletions, and lookups. This makes them indispensable in dictionary implementations and database indexing strategies. Collision resolution techniques determine table efficiency, the most common being chaining using linked lists and open addressing, probing alternative slots. Both approaches impact performance under varying load factors. Load factor optimization. As occupancy increases beyond threshold levels, rehashing operations expand bucket sizes to maintain optimal lookup speeds. Monitoring load factor ensures maintaining acceptable performance guarantees. Python's dict type employs sophisticated open addressing schemes with probing variations. While opaque to users, analyzing source code reveals optimizations minimizing collisions and maximizing cache locality. Careful tuning of hash functions prevents clustering patterns that degrade performance. Good distributions spread out keys evenly across buckets, reducing likelihood of cascading probes. Trees. Hierarchical organization of information trees represent hierarchical relationships between data elements through parent-child connections. Binary trees restrict nodes to having at most 2 children, forming the basis for many specialized tree types. Binary search trees enforce sorting constraints. Left subtree contains smaller values, right subtree larger ones. This property enables efficient searching with logarithmic time complexity under balanced conditions. AVL trees, self-balancing variant maintains height differences within single unit, guaranteeing O, log n, operations. Red-black trees, another self-balancing approach used extensively in language runtimes and libraries. Traversal algorithms differ based on visitation order. Pre-order visits root before subtrees, post-order after, and in order between left and right children. Heaps implement priority queues efficiently using complete binary tree structures. Max heaps prioritize largest elements at roots, min heaps smallest, shaping various optimization algorithms. Graph theory applications in modern computing graphs model complex relationships through interconnected vertices. Adjacency matrix representations suit dense networks, while adjacency lists excel with sparse connectivity patterns. Traversals like depth-first search, DFS, explore paths recursively, while breadth-first search, BFS, systematically examines layers of connected nodes. Both algorithms find extensive use in network routing and pathfinding problems. Directed acyclic graphs, DAGs essential for dependency resolution and topological sorting operations. Minimum spanning trees. Kruskal's and Prim's algorithms compute minimal connecting subgraphs for weighted edges. Implementation choices affect scalability. Matrix forms allow quick edge checks but demand O(V) superscript 2 space. List representations reduce memory consumption at cost of slower neighbor queries. Modern frameworks like NetworkX simplify graph manipulations, offering ready-made algorithms for centrality measures and shortest path calculations. Comparative analysis of data structure performance evaluating trade-offs helps select appropriate structures for specific tasks. Time/space complexity metrics guide decisions in critical system components needing high throughput or minimal latency. Insertion benchmarks show linked lists excelling in middle position modifications, while arrays shine for static collections requiring rapid access. Stack/queue behaviors dictate choice for particular sequencing requirements. Search efficiency. Hash tables provide O(1) average lookup times, contrasting with O(n) for unsorted lists. Sorting algorithms. Tree-based approaches achieve O(n) log n, worst-case performance unlike quadratic time lists. Real-world testing reveals unexpected bottlenecks. A seemingly optimal solution may incur hidden overheads affecting overall system performance unexpectedly. Profiling tools help identify hotspots where data structure choices directly impact execution speed. Continuous monitoring ensures architectures remain aligned with evolving workloads. Design patterns for advanced data structures combining basic structures creates powerful composites. Tree structures enhance prefix matching capabilities, while Bloom filters probabilistically test set membership with high accuracy rates. Segment trees manage range queries efficiently, supporting updates and queries in logarithmic time. They prove invaluable for computational geometry and interval-related problems. Radix trees, space-efficient variation of tries handling integer keys through positional encoding. Disjoint set union implements union-find operations with path compression for nearly constant time complexity. Custom implementations demonstrate principles behind these patterns. Writing a tree from scratch reveals intricacies involved in managing branching nodes and prefixes. Adapting existing structures for novel purposes fosters deeper comprehension. Modifying heap operations to support decrease key functionality expands applicability beyond basic priority queues. Best practices for choosing appropriate structures. Understanding use cases informs better decisions. Frequent inserts/delete at ends favor stacks/queues. Random access demands arrays/hashes. Analyzing operation frequencies determines optimal selection. Considering future growth trajectories matters equally. Static structures may become limiting factors if dataset expectations change unpredictably over time. Algorithm requirements. Sorting algorithms necessitate suitable data arrangements for optimal performance. Maintainability. Clear documentation enhances long-term upkeep of complex structures. Benchmarking different options provides empirical validation. Measuring actual runtime performance under realistic loads ensures informed architectural choices. Code reviews help catch subtle inefficiencies early. Experienced peers often spot opportunities for structural improvements missed during initial development phases. Conclusion: choosing the right data structure remains central to developing efficient solutions. By mastering fundamentals and exploring advanced implementations, developers gain versatility in tackling diverse programming challenges. To deepen your expertise, experiment with implementing these structures manually in Python. Practice coding exercises that force you to think critically about spatial and temporal trade-offs in different scenarios.